Hi everyone, today we will be coding the rank data structure and we will be looking at the naive and the succinct implementations of the rank data structure. So, let us begin. So, in this particular Python notebook I have actually already pre-coded the important libraries and all the all the slides that are that will be useful for explaining the demo. So, we are actually importing the important modules like maths, random and the display modules. Next, I'll be explaining what rank data basically what's a rank operation. So, given a array and you are asked to find the rank of particular character in that particular array till particular position. So, that basically means what are the number of occurrences of that particular character till that particular point. And for this demo we will be using the human mitochondrial DNA as a as our data set. That is because it is small and it is the code will run much faster for this, but later on in the end we will be running it over a bigger example and comparing the results. So, if you see the length of the genome here is around 16,000 base pairs, and so next we are initializing a bit vector and we are keeping its initial value as 0, so that the bit vector is 1 indexed and it will be helping us making our implementation much simpler. So, basically what I am trying to achieve using this is so the character that I will be querying the rank for is character A. So, wherever in the query sequence we have a character A, that bit vector will have a value of 1, otherwise it will have a value of 0. And an important thing to note here is that I am basically treating this bit vector as a string and not as a bit string. So, the space requirement for our particular implementation here will be much more than what the state of the art implementations do, and but for the sake of simplicity and explanation, this is like a good starting point. So, what's a naive way of computing the rank? So, it is basically computing the value of the rank at each and every index using prefix sums, and as you can see this is a small example for the same. So, next we will be implementing it. So, what I will be doing is I will be taking a naive rank list and initializing it to 0, and the length of that list will be length plus 1. Basically I am dealing with 1 base indexing, and then I will be iterating over this particular list and calculating the naive rank at each and every index. Now, the value at index I will be computed from the value at index I minus 1 and based on what particular character is present at that particular index. So, if it is 0, then the contribution of 0 will be added, otherwise we will be adding 1 to the result of rank at I minus 1. and that's it. Like this is the code for the naive algorithm for computing the rank, and next we will be finding its space complexity, and the way to do that is now there is a function called a system.get size of, and that will give you the size of that particular list, but that size will be in bytes, and will be converting it into megabytes by dividing by 1,000,000. And so let us see what's the space required by naive algorithm. What is the space required by the naive algorithm, and it comes out to be 0.13 megabytes. And so when we move on to the succinct implementation, we will see that the space required will be considerably less. So what exactly is succinct algorithm? So how it differs from the naive algorithm is that it does not store the pre-computed value at each and every index. Rather than that, it stores it in 3 different levels, and each of the next level is much more finer. Each next level store much finer information than the previous level. For example, if I want to compute the rank at this particular index I in this image, so it will be the sum of the rank computed at till this particular index, which will be which will get from the array named first, then the contribution within this particular window that will be stored in the array named second, and then the contribution in the remaining place in the remaining space that will be stored in the array named third, and next we will be coding it and like comparing the space requirements. Also these values of L and K, they are chosen in a way that the final space requirement for the succinct implementation, it comes out to be sublinear in terms of the input bit string. So for the succinct algorithm, now let us initialize the value of k, and as we saw above that L is k square. Next I will be initializing my first array, first and the second array. So now as you must have observed above that the first array stores the values after every lth index. So the space required is proportional to L length by L. We are padding some extra we are padding some extra value just to take care of the corner cases and make the implementation simpler further ahead. For the second, this particular value will be k, and then I will be filling these arrays by iterating over the bit vector. So now the value of the bit vector at index I contributes to the index at I by L, the seal of I by L, right. So it's basically all these values in this particular window contribute to the head of the window, basically the value that lies at the maximum index of in that particular window scaled by a factor of L. So that's why we will be using a ceil function. And so if bit vector at particular index I it's 0, then you add 0, otherwise you use the value 1, and the same thing you do with the array second, but over here the factor basically instead of L you are using the value k. Now if you observe above that in the second array all these values they are actually kind of so the every next index also stores the values of the previous indexes. So but like, and that's true also for the first array. So but what we are doing in this implementation is that we are actually storing the values only in this particular window, in this particular index, only in this particular window, in this particular index. But for this index we want the values that have occurred, we want all the values that have occurred before this. So next we will be taking care of that case. So if I mod k is 0, then my second of so I take the value that has been stored in at the previous index and add it to the present index, and that basically takes care of that way. I am actually saving the values that have occurred so far in that particular index and not just in the previous k length subarray. So the same thing we will be doing with the first array, but that will be when the indexes are divisible by L. So for that now one final observation that has to be made in this implementation is that at all the points where we are computing the value for the first array, the value of the second array is initialized to 0 or re-initialized to 0, because we do not want the contribution to so if we want to calculate the value at this particular index I, we do not want the contribution of both the arrays first and second till this particular point, right. We just want the contribution of array first till this point, and from there onwards we will be taking the contribution of second array. So in order to take care of that, whenever I mod L is equal to 0, then the corresponding index in the second array will be initialized to 0. So this finishes the implementation of the first and the second array. Next we will be implementing the third array, and so the third array is basically a dictionary that saves the prefix sum values for all the bit mass of size k minus 1, and for doing that we will be iterating over all the values in that particular range. So we will be iterating over all the bit mass and then naively computing the prefix sum values. So For every bit mask I am saving those prefix sum values in a array called p third, and now you iterate over these bits in that particular bit mask, and so we take the prefix sum value, and over here. So now before coding this, I'll explain how much how will be like getting the bit at that particular index. So for example, consider this particular bit mask. Suppose you shift it towards the right side by one digit, so it will look like this. Then you further shift it to the right side by one more digit, it will look like this. You do that again, and then you finally do that, and you'll reach back to the original bit mask. And what you observe here is that when you shift it towards the right and take AND with 1, or try finding its least significant digit, that will actually give you the value of bit at a point like at index starting from the right direction. So when you don't shift it by any index and you AND this particular value with 1, that will give you the value of the least significant bit, that is 0, right. When you do it here, that will give you the value of the second least significant digit or least significant bit, that is 1. You keep doing this, and you will get 0 here. So if you check these particular values, this will actually represent the original string 0 from left to right in the left to right order. So 0 1 1 0. So that, so rather than iterating over the bit string, we directly compute it using this manner, and because the bit operations are very fast, and this will take just a constant amount of time, rather than iterating that would have taken linear time in the length of the bit string. So what I will be doing is I will be so what's happening here is I am shifting it by k minus 2 minus j times, because I want the value starting from the most significant bit and not from the least significant bit. And after I have computed this, I will just append this pre-computed result for the particular bit mask to the main result, and this gives me the this actually finishes the implementation for the succinct algorithm. Next we will be computing the space requirement for the same, and let us represent that using a variable called s space, and the way to do that is same as we did before, using a function called system dot get size of. Now the space over here will also incorporate the space required by the bit vector, and which was not the case for the naive implementation. And system dot get size of bit vector plus get size of first, get size of second plus third. Next we can just quickly print what this thing is. Again we want the result to be in megabytes, so we will divide this thing by 10 raised power 6. And parallelly we will also compare what's the relative space requirement of the succinct versus the naive implementation. So, succinct algorithm take n space divided by s space less space as comparison to naive algorithm. So, we can just print this thing and check our result. So, as you can see, it takes around 3.5x less space in comparison to the naive implementation, and which actually shows the importance of such succinct data structures. And these data structures are basically used in other applications that you will study further ahead in the course, like Burrows-Wheeler transform. And there are other there are other important applications where you need to store a lot of data in less amount of space, ensuring that you are able to query this data in roughly the same amount of time that you could have done by storing it in a naive manner. So, finally, we will be comparing the output of the naive and the succinct implementation and checking that whether our implementation is correct or not. So, I have already pre-coded the stress test here. So, what I am doing here is that I am appending some extra zeros towards the end of my bit vector. That is done in order to ensure that when I query the result from the third array, that is a dictionary, my basically those many number of values are present in the bit string itself. So, it can happen that in the endmost values, like this particular range itself does not has k minus 1 values. So, in that case it may lead to segmentation fault in the implementation. So, in order to just avoid that, I have already considered it beforehand. Otherwise, we would have to use if else condition, and that would have made this implementation bit more like clumsy, and it wouldn't have like it would have been a bit hard to understand. So, next I will be checking over 10 raised power 6 queries which are generated at random, and I will be comparing the time as well for both the implementations, time as in the cumulative time over all the queries. So, how we query the succinct rank, query the for the value at a particular index in the succinct rank data structure is by first querying over the first array, then over the second array, and then over the third dictionary. And you can verify this particular piece of code that it actually works. So, what is happening in the third dictionary, the first two values are like trivial, which are being showed in the image above, but for the third one what we are doing is we are first of all finding the bit string in that particular range, in that particular curly brace range up to index I, and then we are calculating the prefix sum till that particular ID, that particular index mod k value. So, you can sit over it and think about why it works. So, finally, we are also checking that both the results that we get from both the implementations are matching, and we compare the time requirement for the succinct versus the naive implementation. So, let us run this cell. So, currently succinct algorithm is taking 6x space with respect to the naive algorithm, and that is because the size of the bit vector itself is dominating over, like that has a major contribution here, because the bit string itself is small. But when you move on to bigger examples, then you will see that this value will reduce further, and in order to show that, I have already pre-coded this script for a bigger example. So, let us run that thing. So, the first few cells are exactly the same as compared to like in comparison to the previous script, but in this script we are taking an input of length 10 raised power 6 and not 16,000. So, that is a roughly like 50 times increment over the previous input, and so the bit vector I am taking is taken at random, and that basically does not affect the output. So, the space required over by the 1 second. It is around 8 megabytes, and for the by the succinct implementation it is around 2 megabytes. So, kind of 4x gains over here. And finally, we will find the time requirement, and what you observe is in comparison to 6x time, now we have been able to reduce it to 1.7x time, and as you move further it will further reduce, and like this much, like 2x 3x time is still fine, but most of the times in the big data applications the space is a bigger problem in comparison to the time. So, what I will conclude this demo by saying that in the present era, when where the data is like humongous to process, these succinct data structures are very important in order to save space, ensuring that the time requirements are comparable to the normal methods that would require a lot of extra space. Thank you.